without the absolute value goes to 0. You see in the if-then statement, what we need to do is assume the first part of that statement is true and try and use that to conclude the second part, or the statement B. So what I'm going to do here is I'm going to assume that this is a true statement. Any arguments on that? It's true rather trivially. Observation. But you see, by doing that observation, do you see I could use my assumption along the squeeze there and prove the result?
Mm-hmm.
That's all it amounts to.
So how often will this actually be useful? Because it's not that much easier to solve the absolute value.
It's not, and it's going to become useful later when I prove some other stuff. So like I said, you're not actually going to solve any problems where this in itself is useful. So that's why I don't want to spend a whole lot of time on it. I just want you guys to be aware that if you take the limit of the absolute values and it goes to 0, you're guaranteed that the thing without the absolute value will go to 0. Because there's going to come a point at which we distinguish between convergence and absolute convergence. And that distinction is going to come into play with this.
So you can't go the other way?
You can't go the other way. No,
You can't what?
You can't go the other way. In other words, there's no guarantee that if the limit goes to 0 without the absolute values, then the one with the absolute values will go to 0.
You can't.
Nope. And this is going to come into play even more with series, because with series you start adding these things up, right? And if you think about it, if you start adding it up and some of those terms are negative, then that subtracts out from the overall sum. Whereas if you start absolute valuing everything, you're not going to have the same ability to subtract things out. So we are going to see that play in. But I want to get into the pathologies later, but one of the things you're going to see happen here is when we look at the sum, you know, the sequence is an infinite set of numbers. So when you start adding up an infinite number of numbers, things get a little bit strange. Like, for example, it's not necessarily commutative. You guys know that 1 plus 2 plus 3 is the same as 3 plus 2 plus 1. It's silly to even say that, right? But when you start adding up an infinite number of numbers, I'll show you that it is possible, if you rearrange the order in which you add them, you can get a different answer. So because of those types of issues, we have to be very, very careful about this notion of absolute convergence, because it turns out that this idea of absolute convergence tells us when we can interchange things and get the same value versus when we can't. So you're going to see this get kind of built upon as I go through in the next week or so of lecture. All right, well then let me talk about bounded and monotonic, and then we should be pretty much done with sequences.
So how come for the sets that you don't have an arrow symbol?
I could,
You could
I
do-
could, sure.
So in the first one, is m a function?
No, they're constants, thanks for bringing it up, Christian, yeah, these are constants, in fact, they have to be constants, so here M and N are constants.
I knew n was a constant because we had used that.
Yeah, it's capital N is also. So the idea is if you can put a ceiling and a floor on your sequence, both a ceiling and a floor, then we call it bounded. So for instance, these pictures here, and realize with these pictures, there is a ceiling because this is not just riding up the y-axis because this starts at n equals 1. In other words, you can't get infinitely close to 0. When you start a sequence, it has a starting point. Maybe it starts at 0, right? But you're not going to get infinitely close to 0 and have it shoot to infinity. So you see for these sequences, you can put a ceiling and a floor on it. So we refer to those as bounded sequences. So if you can bound it from above and bound it from below, then it's a bounded sequence. These M's and these N's aren't unique. That's another point to make. Because while this is an appropriate ceiling that I drew in purple, do you see that this green also qualifies as a ceiling? There are such things as the least upper bound and the greatest lower bound. We don't make that distinction in this class because we don't need it for the theorems that we use. But you see there's going to be there's going to be an upper bound for which you can't go lower than. And that bound which you can't go lower than is called the least upper bound because there are bounds which are higher than that. But this doesn't make a distinction. As long as you find a bound from above and a bound from below, whether it's the best bound or not, you can then say with confidence that it's a bounded sequence. Everybody okay with that definition? All right. Then we also have the notion of what it means to be monotonic.